Welcome back, students. Let's continue with the chapter that is S block elements. And in this chapter, let's continue with the next topic. In the last topic, we have discussed about the physical properties and the other atomic properties of the alkali metals. Now moving forward, and here we are going to discuss the chemical properties of the alkali metals. Okay, here we are going to discuss the chemical properties of the alkali metal. So, in the chemical properties of the alkali metals, we are going to discuss first the reactivity towards the air. Okay, how the alkali metals behaves with the air. So, the alkali metals tarnishes in dry air due to the formation of oxides, which in turn reacts with the moisture to form the hydroxides. Okay, so what happens when the alkali metals reacts with the air? So they react with the oxygen which is present in the air to form the oxides, and further when this oxides reacts with the moisture, okay, present in the air, then they forms the hydroxides there. They burn vigorously in oxygen, forming oxides. Lithium forms monoxide, sodium forms peroxides, and the other metals forms the superoxides. What are the superoxides? The superoxides are the O2 minus ions, where one oxygen is having 1.5 minus 1 by 2 oxidation state. Okay, and is stable only in the presence of large cations such as potassium, rubidium, and cesium. Okay, so if we are going to see the reactions here, then the reactions of different alkali metals with the oxygen is like this. If four lithium ions are reacted with O2 which is present in the air, then the formation of 2 LiO2, that is lithium oxide. Okay, Li2O. Okay, here you can see that the oxygen, it is acting as a central atom and two lithiums are attached with it. Okay, two lithiums are attached with it due to presence of two lone pairs here. The structure of this atom, this particular compound, will be somewhat like a bent shape structure. Okay, so lithium oxide, it is a monoxide here. Okay, you can see it is a monoxide. One oxygen is combined with two lithium metals here. Next is the reaction of sodium with oxygen. Okay, sodium with oxygen. So when two atoms of sodium reacts with oxygen here, they form sodium peroxide. Okay, sodium peroxide, that is N2O2. So here two oxygens are combined with each other, and two sodium, they are forming a covalent bond with the oxygens here. So here we can see that the charge on oxygen is -1 on both the oxygen. So therefore they are termed as peroxide. So here it is sodium peroxide. With the other atoms, with the other compound, the compound which are found with the higher elements which are present in the alkali metals, that is potassium, rubidium, and cesium, which are very large cations, there the formation of superoxide will take place. Okay, and here the reaction will be M, which can be either potassium, rubidium, or cesium plus O2. It will give MO2. Okay, here in all these oxides, the oxidation state of the alkali metal is +1 only. Okay, and lithium shows exceptional behavior in reacting directly with the nitrogen of air to form the nitrides, which is termed as lithium nitride. So hence a differentiate or exceptional reaction can also be seen here by lithium, which can react with nitrogen directly to form lithium nitride, while the other members of the alkali metals does not show this reaction. Also, because of their highly reactivity towards the air and water, alkali metals are normally kept in kerosene oil. Okay, they are generally kept out in the kerosene oil because the reaction is very vigorous, and we cannot the reaction can be controlled only when it is been stored in the kerosene oil. Next, let's see this question which is asking here: what is the oxidation state of potassium in KO2? So here, if I am going to see the structure here, in the case of KO2, here you will see that the oxygen, okay, the oxygen per oxygen, okay, each oxygen here, they are forming one bond with each other and one bond with potassium here. So due to this reason, what will happen? They both will have minus 1 by 2 oxidation state, and the potassium will have plus 1 oxidation state here. So hence, the answer here it will be, since the compound is neutral, therefore the oxidation state of potassium must be minus 1, as O2 is having the charge of minus 1 only. So hence here the answer will be that the oxygen, potassium here in the superoxide, potassium superoxide is having the oxidation state of plus 1 only. Let's move further, and in the next we are going to see the reactivity of alkali metals with water. Okay, reactivity towards the water. So the alkali metals react with water to form hydroxide, okay, and dihydrogen. So when alkali metals are reacted with water, so here the formation of M plus ion, that is the cation, will be formed out here, and the anion which is formed out here, it is OH minus from the water. It will get attached to the cation to form the hydroxide, okay, metal hydroxides. Here M can be any of the alkali metal, that is it can be either lithium, sodium, potassium, okay, it can be any of them. It may be noted that although lithium has most negative electrode potential value, okay, its reaction with water is less vigorous than that of the sodium, which has the least negative electronegative value. Among the alkali metals, this behavior of lithium is attributed to its small size. Okay, due to presence of very small size of the lithium, we will see that it is having a very high hydration energy, and the other metals of that group reacts very explosively with water, while the lithium does not show that particular nature. They also react with proton donors such as alcohols, gaseous ammonia, and alkynes also. Okay, they also react with the proton donors such as the alcohols, the gaseous ammonia, and the alkyne groups here. Next, reactivity towards the dihydrogen. Okay, how the alkali metals react with the dihydrogen. So with the dihydrogen, the alkali metal reacts at about 673 Kelvin temperature, while the lithium reacts with dihydrogen at 1073 Kelvin temperature to form hydrides. Okay, to form hydrides. All alkali metals forms hydride. Okay, no exception is there, and all are ionic compounds. Okay, they all are ionic solids with very high melting points. So here you can see 2m plus H2, it will give 2mH. Okay, it will give 2mH, that is the metal hydride. Okay, next is the reactivity towards halogen. So the alkali metals readily reacts vigorously, okay, very vigorously with the halogens to form ionic halides, that is Mx, okay, where M will be the alkali metals and X will be the halogens here. However, lithium halides are somewhat covalent. You can see that the lithium halides which are formed, they are generally covalent, but the other metals, other alkali metals halides are ionic. Okay, it is because of the high polarization capability of lithium ion. Okay, here the lithium ion can highly polarize the electron cloud there of the anion by cation, and this particular the distortion of the electron cloud of the anion by the cation is called the polarization, and this property is present in that of the lithium ion, and due to which the covalent bonds property is more in the lithium halide as comparison to that of the other metal halides which are formed in by the alkali metals. The Li plus ion is very small and has high tendency to distort the electron clouds, okay, around the negative halide ion. Since an ion with large size can be easily distorted among halides, lithium iodide is the most covalent in nature. Okay, we can see that the iodine is the largest of the halogens, and hence in iodine we can easily see that it is having the largest Li is having the largest covalent character as comparison to that of the lithium bromide. Okay, then the sorry, here the sign will be just opposite, that is it will be the lithium iodide is having the largest covalent character as comparison to that of the lithium bromide, as comparison to that of the lithium chloride, as comparison to that of the lithium fluoride. Okay, so lithium fluoride will be highly ionic. Then lithium chloride will be more covalent as comparison to that of the lithium fluoride. Okay, like this the series will be continued out here. And um, due to this reason only here we can conclude this due to the increasing size of the halides here, halogens here. Next is the reducing nature. Okay, reducing nature. So the alkali metals are strong reducing agents. They itself get oxidized and reduces the other elements which are present in front of them. Okay, lithium being the most and sodium being the least powerful. Okay, lithium is the most strong reducing agent, while the sodium is the least reducing agent. Okay, it is having the least reducing nature. The standard electron potential, which measures the reducing power, represents the overall change. Okay, here the standard electrode potential, which measures the reducing power, represents the overall charge here. Here, metal solid when converts to metal gaseous. This is known as the here the sublimation enthalpy will be released out here. Okay, means the energy which is released out in order to convert the solids into gaseous, it will be sublimation enthalpy. Okay, it will be absorbed by the metal solid. Next, metal gas. Okay, it will release one electron in order to attain a positive charge. Okay, to form a cation here, metal cation. Now this metal cation can react with the water due to its high hydration enthalpy. Okay, with the small size of its ion, lithium has the highest hydration enthalpy. Okay, due to the small size of lithium, we will see that it is possessing the highest hydration enthalpy. Okay, and the value of the high negative electrode potential will be also there, and it is having the high reducing power also. Okay, due to smaller size, high hydration enthalpy, and high negative electrode potential, the reducing power of lithium will be very very high there. Next, a question is being asked out here that the electrode potential of Cl2 or the chloride ion is plus 1.36. For iodide it is plus 0.53, and for silver it is plus 0.79. Sodium is minus 2.71, and for lithium it is minus 3.04. Arrange the following ionic species in decreasing order of reducing strength. That is I minus, Ag, Cl minus, Ni, Na. Okay, we have to arrange the following according to their reducing strength. Okay, according to their decreasing reducing strength. So here we can see that as the negative value, okay, the negative value for the lithium, it is highest. Okay, it is highest. So here we will see that lithium will be the highest reducing agent here, and after that the number for the sodium will come because it is having the value minus 22.71. Okay, this minus sign shows the reducing potential and the plus sign shows the oxidizing potential. So here it shows that the chloride and the iodide are having the highest oxidizing potentials, while the sodium and the lithiums are having highest reducing potential. So hence the series will become Li, then comes the Na. Then here we will see that the value for the iodide is more. Okay, as comparison to that of the silver, we will see that the iodides are more reducing in nature. Therefore, iodide will come. Then the number will be for silver, and the last will be for the chloride. It means the chlorine is the least reducing agent. Okay, it is the least weakest reducing agent in the given elements here. Next is the reaction of solution in liquid ammonia. Okay, how the alkali metals are forming the solution in liquid ammonia. So here the alkali metals dissolves in liquid ammonia, giving deep blue solution which are conducting in nature, which are very highly conductive in nature. So in reality, what happens when the metals of alkali metals reacts with dissolves in NH3? Here what happens? X plus Y is formed. Okay, and this X plus Y with ammonia, it is nothing other than the molecules of ammonia which has been attached with the formulation here. Okay, so here the electron which has been released, it is also accepted by the ammonia. Okay, and the plus charge which has been attained by the metal ions, they also get attached with the ammonia here to form the to form the complex compounds here. Okay, and the blue color of the solution is due to the ammoniated electrons. Okay, here you can see that the ammoniated electrons are present, which are having the tendency to reflect the blue light, and hence the color of the solution becomes blue here. The solution are paramagnetic and on standing slowly liberates hydrogen, resulting in the formation of amides here. Okay, as slowly the hydrogens will be liberated out, so here slowly the amides will be formed out here, where am denotes the solution in ammonia. Okay, here you can see that MnH2, which shows the solution in ammonical solution it is. In concentrated solution, the blue color changes to bronze color and becomes a dimagnetic. Okay, while in the case of concentrated solution, here we will see that they convert from paramagnetic to dimagnetic, and so blue color of the solution converts to bronze color there, and the dimagnetic nature of the solution has been found out there. Next is the uses. So lithium metal, okay, lithium metal is used as one of the most useful alloys. Okay, lead alloy to make white metals, bearing for motor engines. Okay, with aluminum to make the lithium aircraft parts, with magnesium to make the armor plates. It is used in thermonuclear reactions also. Lithium is also used to make the electrochemical cells also. Okay, sodium is used to make a sodium lead alloy needed to make PbEt4 and PbMe4. Okay, this organo-lead compounds were earlier used as anti-knocking additives. Okay, they were used as anti-knocking additives to the petrols, and that petrol was termed as leaded petrol. Okay, but nowadays vehicles are used lead-free petrols. Liquid sodium metal is used as a coolant in the fast breeder nuclear reactors. Okay, liquid sodium metals is been used as a coolant in the fast breeder nuclear reactor. Potassium has a very wide or vital role in the biological system. Potassium chloride is used as a fertilizer. Okay, potassium chloride is one of the famous fertilizers. Potassium hydroxide is used as a manufacture of soap. Okay, it is also used as an excellent absorbent in carbon dioxide. For absorbent of carbon dioxide also, potassium is being used. Potassium hydroxide is being used. Cesium is used in devising photoelectric cells. Okay, for devising the photoelectric cell, cesium is being used due to its very good photoelectric property. Next, the general characteristics of the compounds of the alkali metals. So, when discussing about the general characteristics of the compounds of the alkali metals, let's discuss about first oxides and hydroxides. Oxides and the hydroxides. So, on combustion with in the excess of air, lithium forms mainly the oxides, that is Li2O. Okay. Also, it can form the peroxides Li2O2. Sodium forms the peroxides and some superoxides also. While the potassium, rubidium, and cesium, they form only the superoxides. Okay. Under appropriate conditions, pure compounds such as MO2, MO2, M2O2, or MO2 may be prepared. The increasing stability of the peroxides or superoxide as the size of the metal ion increases. Okay, is due to the stabilization of the large anions by large cations through lattice energy effect. These oxides are easily hydrolyzed by water to form the hydroxide according to following reactions. Okay, if you are reacting the monooxides with water, then the formation of 2M plus and 2OH minus will take place here. Similarly, if the peroxides are reacted with water here, then also the formation of 2M plus 2OH minus and H2O2, that is hydrogen peroxide, will form out here. Similarly, when the superoxides also are reacted with water, so formation of 2M plus 2OH minus, okay, plus hydrogen peroxide and oxygen will be liberated out in this condition. Okay, so the oxides and peroxides are colorless when pure. Okay, when they are pure, they are colorless, and superoxides are yellow or orange in color. We will see that the superoxides are having yellowish or orange color in them. The superoxides are also paramagnetic. Sodium peroxide is widely used as an oxidizing agent in the organic chemistry. Now, why KO2 is paramagnetic? So here KO2 is paramagnetic because we will see that in the superoxide, O2 minus is paramagnetic, and because due to presence of an unpaired electron in the pi antibonding 2p subshell, okay, of the O2 minus, the paramagnetic property is been transferred to the superoxides also, and hence the KO2 is also a paramagnetic compound. Next, the hydroxides which are obtained by the reaction of the oxides with water are all white crystalline solids. The alkali metals hydroxides are the strongest of all bases and dissolves freely in water with evolution of much heat on account of intense hydration. Okay. Next, halides. The alkali metal halides, that is Mx, the formula, the general formula will be Mx, because +1 and -1 is the charge for the halogens and that of the alkali metals. Okay, so they are forming the formula that is Mx, general formula. All are having high melting point. They are colorless crystalline solids. They can be prepared by reaction of the appropriate oxides, hydroxides, or carbonates with aqueous hydrohalic. Hydrohalic means HX acids, okay? Hydrohalic solutions. All of these halides have high negative enthalpies, okay? They have high negative enthalpy of formation, and the value of formation enthalpy of fluorides becomes less negative as we go down in the group, whilst the reverse is true for the formation enthalpy for the chlorides, bromides, and iodides. For a given metal, formation enthalpy always becomes less negative from fluoride to iodide. We will see out here. The melting and the boiling point always follow the trend, that is, fluorides will be having higher melting point as comparison to that of the chlorides, as comparison to that of the bromides, and as comparison to that of the iodides. All these halides are soluble in water. All the halides which are formed for the alkali metals, they all are soluble in water. The low solubility of LiF in water is due to its high lattice enthalpy, whereas the low solubility of CSI, that is cesium iodide, is due to its smaller hydration enthalpy of the two ions. Other halides of lithium are soluble in ethanol, acetone, and ethyl acetate. LiCl is soluble in pyridine also. Okay, so here we will see that the different trends for the solubility of the metal halides, alkali metal halides. Next is the salt of the oxo acids of alkali metals. So oxo acids are those in which the acidic proton is on a hydroxyl group, that is the OH group. Okay, here the H plus will be released out from here, therefore they are termed as the oxo acids. Okay, now the example can be taken out here for carbonic acid, H2CO3. So here COCOH twice. This is the formula where H is present as the hydroxyl group. Okay, similarly H2SO4, they are also O2SO2OH twice. Okay, so the alkali metals form salts with all the oxo acids. They are generally soluble in water and thermally stable. The salts which are formed, they are generally soluble in water and they are thermally stable. They are carbonates, that is M2CO3, and in most cases the hydrogen carbonate or the bicarbonate, that is MHCO3, also are highly stable to heat. Okay, as the electropositive character increases down the group, lithium carbonate is not so stable to heat. Okay, lithium being very small in size polarizes large CO3 2 minus ions, leading to the formation of more stable Li2O, which is more stable as comparison to that of the lithium hydrogen carbonate, and CO2, which is more stable. Its hydrogen carbonate does not exist as a solid. Okay, the lithium hydrogen carbonate does not exist as a solid here. Next, anomalous property of lithium. In the starting of this chapter also, I have discussed with you that the lithium is having some of the anomalous property because of its small size, okay, and of its atom and ions. High polarization power is also there in lithium, okay, that is the charge with the radius ratio. As a result, there is an increased covalent character in the lithiums, while the other members of the alkali metals are having the high ionic character. Okay, so further, lithium shows diagonal relationship with the magnesium. We will see that the lithium's properties are very similar to that of the magnesium as comparison to that of the members of its own group. Okay, so what are the points which is the difference between the lithium and the alkali metals which are present here? So lithium is much harder. Okay, it is much harder as comparison to that of the sodium potassium. Okay, they are very softer, but lithium is much harder. Lithium is the least reactive but the strongest reducing agent among the alkali metals. On combustion with air, it forms Li2O, that is monoxide, and also it reacts with the nitrites also to form the Li3N. LiCl is the deliquescent and crystallizes as a hydrate, that is LiCl2H2O, whereas other alkali metals chlorides do not form the hydrates. Lithium hydrogen carbonate is not obtained in the solid form, while others are obtained as the solid hydrogen carbonates. Lithium, unlike other alkali metals, forms no ethynide on reaction with ethine. Okay, lithium nitrate when heated with lithium oxide, whereas other alkali metals nitrate decomposes to give the corresponding nitrates there. Okay, 4LiNO3 gives Li2O plus 4NO2 plus O2 gas here. Okay, similarly 2NO3, if it is been heated, so it will form 2NO2 plus O2 gas here. Lithium fluoride and lithium oxide are comparatively much less soluble in water as comparison to that of the other halides and oxides of the alkali metals. So for today, I am concluding the class here only. In the next class, we will start with the similarities between the lithium and magnesium, and we will move towards the alkaline earth metals chemistry. So for today, thank you. We will meet up in the next class.